So Harald and I have a joint presentation today, and we want to talk about the work we do on immersed methods at TUE, and then especially the combined immersed and isogeometric analysis work. So as an outline, I will first give a brief introduction of the kind of things we consider in the group, the applications and the kind of methods. Then in the first part I will be talking about the work we do on scan-based isogeometric analysis using the finite cell method. Harald will then spend about 15 minutes on the work we did on conditioning issues. And finally we will conclude with a few slides where we point out what our state of the art is and what for us the open problems are. So to give you a bit of an overview of the applications that we consider, so we have various projects going on with OC Technologies, which is a Dutch company developing inkjet printers. So there we're simulating both droplet formation and the imbibition of the ink into the paper. And one of the immersed problems there is that these droplets get smaller and smaller, so if you want to model the imbibition, you do have to consider the porous microstructure of the paper, where immersed methods of course are very handy because then you can say in a versatile way represent that geometry. We have various biomedical applications, so together with the guys in Pavia we are working in the direction of arterial blood flow problems. And together with colleagues from Eindhoven, we've been working on trabecular bone mechanics. There's a nice figure of that over here. This is a piece of trabecular bone. Other type of applications that we consider are hydraulic fracturing related. So we consider hydraulic fracturing, say at the mesoscale, a figure that is shown here, where we use immersed methods to actually make a coupling with phase field methods, but then to really recover an explicit representation of the loading boundary so that we can transfer fluid forces onto the phase field model through immersed methods. And also there we want to look at smaller scales where you really are modeling the say extraction of oil on the porous microscale. The final application that I want to address here in this context is work we have going on in photolithography together with ASML, which is a big Dutch producer of wafer stepper, actually the biggest one in the world. So there, these problems revolve all about rarefied gas dynamics. And the work there we are not yet applying in the context of immersed techniques, but that would become relevant when you want to go to nanoporous materials, for example, where the flow through those materials really become rarefied, and you need to look into kinetic theory type of models. So in terms of models and methods, what we do in the group is we work on phase field models, both for multi-phase flows and for fractures and combinations thereof. A lot of the problems that we consider are coupled, so Harald has a lot of expertise on fluid structure interactions, and more recently that kind of work has been extended to elastocapillarity in the context of the paper mechanics. And another branch of models is the kinetic theory, where the special focus has been on moment methods for the Boltzmann equation. In terms of numerical techniques, a lot of our work revolves around isogeometric analysis since the last decade more or less. In many cases that goes together with an immersed technique where we have always been following the ideas of the finite cell method. A lot of the simulations that we do go together with some form of adaptivity, where especially we often focus on goal-oriented methods, so where you try to optimize your mesh versus specific quantities of interest, which relates closely to doing reduced order modeling, of course. And more recently we have various projects going on that relate to stochastic analysis, mainly Bayesian inference, which closely links up with reduced order modeling, of course. So today both our talks will be about the finite cell method and isogeometric analysis. So I can very quickly go over this slide since you all are completely aware of the setting. So the idea is that you have some physical domain here. You know that the omega that's embedded into a bigger domain called a fictitious domain. So for the image-based analysis that we consider here, the one special thing is that also the fictitious domain or the ambient domain has a meaning, because that's typically just a domain that you actually get from your scanner. So that there's a real thing and not an arbitrarily chosen bigger domain. So we have the standard Galerkin formulations all the time, and then in a nutshell what we do is we just build basis functions over the simple domain, and we restrict them to the geometrically and topologically complex physical domain, omega. So we started working with this kind of immersed techniques from the motivated by the needs coming from isogeometric analysis. So specifically what we wanted to do a few years ago was to apply smooth basis functions, B-spline basis functions, to geometrically and topologically complex volumetric domains, specifically the trabecular bone type of structures. And since there are no analysis suitable splines, conforming spline discretizations for that kind of geometries, at least not without resorting to really many patch type of discretizations, we went for this immersed type of technique. So the idea there really is you build a very simple spline basis or structured spline basis over the simple domain, and then you immerse it using the finite cell method to model or to create a basis for your complex domain. Of course, you have to deal with a few issues there, and today I will, or we will be talking about two of those aspects. So the way we do the trimming and the parameterization of both the volume and its boundary, and the system conditioning. So that is the first part of this presentation. So how do we work with scan-based analysis, and how do we get stable results for that? So both in solid mechanics and fluid dynamics. So this is the typical setting that we have here. So we either want to say have a block of material and we want to know average material properties for it, or we sometimes consider the complement of the domain and we want to know how the fluid flows through that domain, of course with the idea of deriving things like homogenized permeability coefficients. So if you think about the problem formulation, the input is always a voxel file consisting of millions of voxels. In terms of geometry and topology, these are the kind of the domains that we have, so very complex. And they're always volumetric, especially with fluid flow models. It's often very hard to make a representative 2D specimen. So you typically have to consider the 3D case in order to get meaningful results. So the simulation strategy that we have for this is that we take the voxel data, then we first do a smoothing operation to get a nice representation of the boundary. We then use a finite cell strategy to get a parameterization of the geometry, and finally we just run the immersed isogeometric analysis framework on that. So I want to quickly go over those three steps and highlight some of the things we did there. So the geometry extraction, basically how it works is you take your grayscale data, here shown in 2D, and then what we do is we transfer that grayscale data into a B-spline function. And how we do it is we create a uniform B-spline patch over the voxel domain with the same resolution, and we just convolute the coefficients of the B-spline through the simple operation shown here, which basically is just you weigh your grayscale data with the B-spline basis function. So it's a very simple averaging procedure. And then once you have obtained the smooth B-spline representation of that raw data, you just do the trimming operation with the bisectioning scheme, as I'll show it later, to get the smooth geometry out of it. Well, the idea behind this technique is the following. So first of all, it's explicit, so you can do it very fast because it's just about computing those integrals. But it has some nice properties. So first of all, when you go to B-splines of order 2 and higher, you get a smooth representation of the boundary. What you can show easily is that you conserve the intensity in the operation. So the average grayscale value of the bottom figure is the same as of the top figure, which is nice because that preserves the meaning of the threshold number that you typically get from your scanner. So typically you have a threshold for that one and you want to transfer it to there. The operation is locally bounded, so that means that you don't get Gibbs wiggles around the interfaces. The B-spline smooth it out quite smoothly. And a result that we are particularly happy with is the following. So if you think about the operation as a convolution operation, and you look at the convolution kernel, then what you see is that actually it's in the limit of p going to infinity, but for high p, it behaves as a Gaussian blurring operation. So essentially, where then say the radius of the Gaussian well depends on the order of your spline. So the higher the spline order, the more you smoothen out, of course. And you see that here. So this is the kernel shown in one dimension. So you see the typical Gaussian shape here, and this is the typical effect that you have there. So evidently, what you do is you smoothen out sharp features, or say staircase-like features. But you have to watch out, because if you make the order too high and you start violating the Nyquist criterion, you of course also can lose you can lose real geometric features. So basically, it just means that your scan should have sufficient resolution to detect the geometric features, but that's of course not always the case. So it's something to watch out with a little bit. So smoothing out too much, you might lose geometric accuracy. So the integration then. So what we do is we have this bisectioning scheme where you subdivide the cells recursively until a predefined level, and then at the closure, the traditional schemes are there to do a masked uniform scheme or something like that. But in our simulations, we always value to get a boundary representation of the trim boundary, and for that reason, what we do on the smallest level is we do a triangulation scheme there. And then, of course, when you have the triangulation scheme on the smallest level, it's a matter of just extracting the boundaries of those triangles to create a parametrization of the immersed boundary. So we've been doing that already for quite a long time, and initially all that work was based on Delaunay triangulations. So how that worked in 3D was the following. So let me first say in 2D everything works perfectly all the time, and 3D not so much. So let me show you a little bit what goes on there. So in 3D what you do is you have this typical, say, subcell, integration subcell. So we compute the level set values at all the vertices, we compute the intersections, and then we use two Delaunay triangulations, one for the non-negative points, which gives something like this as a triangulation, and then we have another one for the non-positive points, which gives a triangulation like this. So the idea is that you have parametrizations for the two sides of the domain. So you could do, you could model, for example, the interface between two solids or something. Anyway, it's an interface type of problem that you can consider now. But the problem here is that if you do this in 3D with Delaunay, then you will find out that because of the convex hull property of Delaunay, the interfaces between the two domains do not match, because this is how you triangulate the interface from the one side, and this is how you triangulate it from the other side. So you have a mismatch there, and then if you want to apply interface conditions, you run into a problem because you do not have a unique parametrization of the interface. So that was problematic for us, and for multiple reasons. And we tried something else. So quickly the pros and cons. So of course the good thing about Delaunay is that implementations exist, but we have the non-matching interfaces. And another problem that I wanted to highlight here is that is the following: that what I'm zooming in here on one of the Delaunay or two of the Delaunay simplices here on the left, and what you see actually that what Delaunay does is this. Face here of the original cube, which is untrimmed, it's just a regular face. Of course, it still gets triangulated by the Delaunay scheme, because the Delaunay scheme only returns tetrahedrons to you. And that is a problem that was a problem for us when we want to do consecutive trimming operations. So say we trim this one again, then how we do that is we have all the tetrahedrons there, we trim it again, and we interpolate the level set functions on those nodes. But now the problem that you get is that that interpolation on this face here is based on the two triangles that we have in that face, where on the neighboring element, which was not trimmed, you just have the original rectangle there, and you get a different kind of trimming that you do. And then you get, in the second trimming operation, you get a mismatch between two neighboring cells. So that, that didn't work out for us. Also, we just had a lot of implementation problems or algorithmic problems. So mainly, what you see with these interface extractions is that the standard algorithms, they return flip normal vectors and these kind of things, and the code just becomes horrible at some point if you need to apply all the add-on fixes. So we wanted to do something else, and this is what we did. So we call it the recursive midpoint desolation. So what we do is we have this recursive scheme where we first compute the level set values, then we trim all of the edges, so the topologically one-dimensional structures. We trim all of them, we identify the contour, which here is formed by those two points, then we compute some midpoint, and then we extract all those interfaces to the midpoint, like this, 1, 2, 3, and 4, and we create a tessellation like that. And if you now do the same thing for the opposite side, of course you get here a uniquely defined interface, which you can just extract, and by definition the thing is compatible between the two sides. So how do we do a 3D? Well, we take the cube, let me represent it a little bit differently. So if I unfold it, we do it recursively again. So for each of the faces in the cube, you apply this scheme. That gives you then tessellations of all of the schemes. You get a loading, now here you get a contour, a trimming contour. We again compute a midpoint for that contour over there, and we extract or we extrude all the faces toward that midpoint. And in that way, you get tessellation of the two sides, and you get your interface from it, which is again then uniquely defined between the two sides. So it's compatible, and what you see here, let me see, I don't have it. And what we do is say this original face here that you had on the left, which was not trimmed, we make a pyramid element out of it. So we just extrude that square into that midpoint, which gives you a pyramid with a square base, and we don't have this problem of multiple consecutive trimming operations. Little downside is that sometimes we end up with more triangles than we do with the Delaunay scheme. So that is a little bit of price that we pay there. And a few more slides on the recent work that we did on applying this kind of schemes in Stokes and Navier-Stokes. So one of the results that we already published last year is that if you apply the standard isogeometric imsub-stable spaces for Stokes, so Taylor Booth and Ravier Thomas and Nederlek and all those spaces, if you apply them directly in the finite cell context without doing anything special, you end up with these oscillations in the boundary. And these oscillations, they are not related to conditioning, because they also appear on cut cells that are pretty big, but they're simply related to the InfSub stability. So just on these cut cells, the InfSub stable spaces do not stabilize enough, or do not stabilize in the way they do on conforming grids. So we get pressure wiggles all over the place. So that we've been addressing, and we've done that using the skeletal stabilization. So the skeletal stabilization, we do various things there. So let me point out. So first of all, what we do is we take equal order, or the identical spaces for pressures and velocities, and then we circumvent the InfSub condition, or the InfSub stability condition, by supplementing the formulation, the immersed formulation, with the pressure penalization, which is a continuous interior penalty type of penalization, with that difference that we apply it to CDK-1 regular splines, which means that we only penalize the highest order normal derivatives of the pressure space. Where gamma is then, of course, the penalty parameter that you need to select. Well, evidently that is, once you have set up that whole framework with the skeleton and everything in there, it becomes pretty trivial to also add the ghost penalty stabilization term to circumvent ill conditioning issues, and also velocity wiggles at the pressure boundaries. And what essentially it means is, so you add also a penalization term on the highest order velocity derivatives, and then in your Nietzsche term that you have added, you're now allowed to, so your Nietzsche stabilization, you're now allowed to scale it with h, which is now the mesh size of the untrimmed mesh rather than the mesh size of the trimmed mesh. So that helps a lot in the conditioning aspects. And Harald will get back to that a little later. So we did some convergence tests. How am I doing with time, Gavin? Not good. Okay, I'll speed up a little bit. Again, so we show optimal rates of convergence for all kinds of orders. We've looked into, of course, the sensitivity of the stability parameters, and what you see there is that since we mainly penalize the pressure coefficients all over the volume, the velocity convergence is hardly affected, but you see an effect on the pressure error. So still you have optimal rates of convergence in the pressure, but of course the magnitude of the error is influenced by the parameter. Having said that, there is a range of parameters for which you pretty much are insensitive to those parameters. So a quick look at the sparsity. So this figure requires a little bit of explanation. So on the left you see the Lagrange, a Lagrange discretization matrix for Navier-Stokes, and on the right you see the one for the B-splines with the skeletal stabilization. So at first this one looks much more dense than this one, but you have to look carefully because it's done on the same mesh, which means that effectively this one contains 3 times as many degrees of freedom, so you have 3 times more Lagrange basis functions than you have B-spline basis functions. And closer inspection shows that actually the number of off-diagonal bands is equal to p plus 1 in the case of B-splines, because of the higher order continuity between the spines, and it's equal to 2p in the case of Lagrange. So that means in terms of the sparsity structure, there is actually a fundamental advantage here to using the, say, optimal regularity B-splines. So of course for p equals 2 is shown here, the difference is not big because it's the bandwidth here is 4 and here it is 3. But clearly with increasing p this problem becomes more pronounced. So quickly the simulations that we've run. So we've looked at flow through a piece of sinter glass based on a micro CT scan, and we made a comparison between more traditional voxel methods and our technology. And then of course just by looking at the geometry, what you realize here is in these kind of flow simulations, the surface area is important, because that determines how much friction you have also on the fluid, of course. And then what you see is actually that for the voxel mesh, the surface area is about 50% larger than it is for the immersed grid, just because of all the staircase type structure representations that you have. So that's already a big difference. And then if you look at the simulation, so we ran a voxel method, so a finite volume type of method in Fluent, and we compare it to our result. And there you see basically for the pressure here, which is the pressure jump over the block is prescribed from the inflow to the outflow boundary. So you see virtually similar results, but important here is to realize that in these kind of methods, there's a direct coupling between geometry and discretization mesh. So this one has as many degrees of freedom as you see voxels here, whereas this simulation, it had 12 by 12 by 12 B-spline elements. So it has about, in this case, I believe 20 times fewer degrees of freedom than the result shown here, whereas the result is pretty much identical. Of course, from a computational effort point of view, the comparison is a bit harder because the operations that you conduct there on the right are a bit more intensive than on the left. But there's a fundamental difference in the sense that in this setting you can talk about refinement and convergence behavior, whereas here you cannot. So the streamlines as a final illustration there, you see, the post-processing is not quite identical, but you see really that with the coarse mesh, you're able to recover the most important flow features. So to summarize this part quickly, so we have this image-based analysis strategy and the workflow compatible with the final cell method. At the moment we are focusing on applying that in the Stokes and the Navier-Stokes setting, where we have very good results coming in. also due to the ghost method stabilization that we do. And with that, I would like to give the floor to Harald, who will talk about the conditioning aspect of this.
Okay, so thank you also for the introduction, but of course I would like to thank Ricardo and Ade for organizing this workshop. Maybe a good starting point for me would be to say that if you would have asked me 10 years ago whether I would ever go into immersed methods, I would have said no, and absolutely impossible. But now 10 years later, I'm standing here in my group where actually it's one of our main efforts, I would say. For me personally, I got there by a detour, I would say. Maybe it started with IGA in some sense, because it has this very natural dissociation between the approximation space and the mesh. For some people working in finite elements, they never made this connection. They would say, you know, the mesh is just there to do integration. It has nothing to do with the approximation space. For me, for some reason, it was always connected. Now with IGA, it becomes a bit more dissociated. The mesh is really, it is not that intimately connected to the approximation space anymore. And now if you go to embedded, at the end of the day, if you combine it with IGA, well, you just generate a space which is completely distinct from actually the geometry you want to resolve. That's the whole framework. So, as Clemens pointed out, you have a very natural dissociation between, say, the resolution of your approximation space and the resolution of your geometry. These are not really connected anymore. And for instance, in the context of this imaging-based type of analysis, that makes it very powerful. And so traditionally, people have been working for decades on these voxel-based methods, where you have this one-to-one connection between geometry and say, the approximation space. With these CUT-FEM or FCM type techniques, this connection is not there anymore. Okay, but that is a starting point. So I will talk a bit more about the conditioning, which was already, Santiago already mentioned it briefly, and the things we have been doing there. So basically with immersed, you do make these cuts, and ultimately they will end up in ill conditioning of the system. So the approaches that have been around are these fictitious domain type approaches, or fictitious domain stiffness, that you can use partly to resolve ill conditioning, basis manipulation, function removal on the one hand, linearly constraining, so basically aggregating elements, web spline techniques, the ghost penalty method, that's something we are very happy with actually, which has been serving us extremely well, which you can think of as a weak type of aggregation in some sense. And then of course, and that's the thing I will be talking about, is preconditioning strategies. Diagonal scaling, that's a no-brainer, 101 I would say. That's been working very well. We've been extending that to what we call SIPIC, so that's symmetric incomplete permuted inverse Koleski. I'll get back to that in a moment. And the more recent addition is called CBAS, connectivity-based additive Schwartz. So if we try to retrace where the ill conditioning actually comes from, basically, of course, we represent approximation functions by means of coefficients, right? At the end of the day, it's all linear algebra or discrete algebra. So there's an equivalence between finite element functions on the one hand and the vector that you use to represent those. Once you go through the weak formulation, that's restricted to the linear case in this situation to make it simple, then at the end of the day you have to solve a linear algebraic system, and you care about the condition number of that system, which is just the product of the norm of the matrix itself with the norm of the inverse. Or for a symmetric matrix, that would just be the ratio of the largest eigenvalue to the smallest. Now, if you do the analysis, then basically, if you want to determine the largest eigenvalue, or basically the norm of the matrix itself, then typically what you will find is that corresponds to a function which has the highest periodicity that you can represent in your discrete space. Right? So that would be the standard one. So for the norm of the inverse of the matrix is induced by a function which has the lowest periodicity. Right? So So that typically gives you for second order elliptic equations, that gives you the h squared growth, if you will. Now the issue is if you go to cut elements, so for the highest order it does, so for the norm of the matrix itself it doesn't change, but for the norm of the inverse it changes, because basically I can now form a function which has on this cut domain, which has, essentially it has coefficient 1, but it has very small support. Right? So the norm of the inverse is no longer determined by the function with lowest periodicity, but basically it's determined by the smallest cut now. The function with the smallest volume fraction. If you go to a higher order, that becomes even worse, right? So again, you can form functions with coefficient 1, which have extremely small support. Right? So for linears, it's reasonably controllable, but if you go to higher order, that becomes even worse. And that's actually where the scaling relation comes from. So as Sante already showed it, so basically the condition number now scales with the smallest cut, or the smallest volume fraction, to the power minus 2p. So here's the order dependence, plus n, where n is something which is 1 or 1.5 or a half, which depends on basically the stabilization that you introduce. But the most important one is actually this 2p scale. So as an experiment, just to show that you also observe this practically, if we do it for Stokes, and we basically the test case that we do, just go back here, is that we take the square and we rotate it through a background mesh. Then of course for all the different orientations you can determine the smallest volume fraction, you can determine the condition number, and if you would then plot that for different orders, you see exactly this behavior. Right? So in an actual computation you see exactly this type of scaling. It follows from the analysis for the Laplace operator, that you see it directly back also in Stokes, and in fact also for Navier-Stokes. Right? So this is Navier-Stokes, low Reynolds number, but still it's the exact same scaling. It all has to do basically with this, with the elliptic part of the operator. So how does one actually resolve that? So the main issue is actually that you would have functions which are in some sense way smaller than the corresponding coefficient. So the idea of preconditioning is essentially that you do a rescaling of the basis. At least it would be step 1. So you introduce a new basis, which is formed by a preconditioning operator acting on the original basis, in such a way, of course, that they span the same space. And then you have to form this matrix S that you have over here in such a way that you avoid the conditioning problem. Now, if you look at what it means in terms of the linear algebra, basically you have to say you apply the same scaling to the test in the trial space, so basically it becomes symmetric in that sense. And in that sense, the manipulation of the basis just in the linear algebra is just a form of pre and post conditioning. So in terms of the eigenvalues, it turns out that the eigenvalues of this system are the same as of this one. So you would want to construct S in such a way that you control the largest eigenvalue of the inverse. That's the thing we need to control, or that means the smallest eigenvalue of the matrix itself. That's the thing we want to bump up and we want to make as large as possible. Here's a zoom in between the original basis. So what you would see is that there is the basis function which has coefficient 1, right? The coefficient, if you will, of the basis function is determined over here. But given that it has very small support, the basis function itself is just is very small. As a result of that, it will induce a norm for the inverse, which is very large. So that's basically that gives you the conditioning. And now the idea would be, step 1 was you just rescale the thing in such a way that the norm of the function is proportional with the coefficient that it has. Just a rescaling operation. This is only part of it. So this would amount to diagonal scaling, just rescaling of the basis function, but that does not resolve all the problems, and this is actually something which has, so the rescaling is something which has been recognized also in the Gott-Feldman community, so of the linears. But actually if you go to higher order, there's a second issue which you need to treat, and that's near linear dependence of the elements on small volume fractions. So that would, in terms of the manipulation of the basis function, that would amount to sort of an orthonormalization process, which you do on pairs or multiples of basis functions. So the main issue is actually this one. If I consider the basis functions, but then restrict it to this small cut that you have over here, then what you would find is that, say, two distinct basis functions will look very similar on this small cut. Right? So on this small cut, everything is more or less linear by low order approximation. So if you have many basis functions for your high order space, all of these basis functions will be nearly linear dependent on the small triangle. So basically what you could do is you would have two different basis functions, right? So this is what one would look like on the small element, this is what the other would look like. Now I could form the sum of them and the difference, and you would find that the difference is virtually zero. Right? So this illustrates the linear dependence that you would have. As a result of that, that's the second form, or the second source of ill conditioning of the system. Now the way to resolve that is actually that you form two new basis functions by orthonormalization. So the new basis function, the first new basis function could be the same one that you already had, but the second one is such that it's orthogonalized with respect to this one. So it's like you take a linear combinations of your previous basis functions in such a way that you put two linearly independent new bases. It's an orthonormalization procedure. So what does that look like? So basically if I look at, say, this small section over here and I zoom in, I have three basis functions over here, the blue one, which is not an issue because it basically has support on a large element, so it will get its linear independence from the fact that it has significant support on the full element. But the red one and the green one are just supported on this single element. And so you will see both are virtually linear on the small element, so they're linearly independent. If you zoom in and you rescale, now in terms of the scaling they're okay, but they're still linearly dependent. So now you need to do the orthonormalization. So you would just retain this one, but this function would be replaced by a function which is orthogonal with respect to the red one. Right? So basically if you do high order, you will not get away with just rescaling. You also need to do some form of orthonormalization on the cut elements. So what does that amount to? So basically the preconditioner that we've been constructing, so at the linear algebra level, would look something like this. It's a lower triangular matrix. STS, that's the thing, that's say, the full preconditioner. But what that thing is supposed to do is basically, it needs to provide you with an approximation of the inverse of the blocks corresponding to the linearly dependent functions. Functions that need to be rescaled. That's actually where the name SIPIC comes from, because basically what you can see over here is that it's just a Koleski factorization of the approximate inverse of the blocks which cause the ill conditioning in the system. And so this is what the SIPIC procedure is. Let's see, so if you have larger multiple functions can be involved, right? So then the blocks become larger. Now you may have situations actually that there's one basis function which occurs in multiple cut elements. Right? So in that case you would get the overlapping blocks. And then what you would find is actually that the preconditioner that you're constructing is nothing but additive Schwarz. It's an additive Schwarz preconditioner, but which is based on judiciously figuring out which basis functions cause the ill conditioning in your system. So once you figured out that at the end of the day what you're doing is just additive Schwarz, that also provides you with an idea how to generalize it beyond symmetric systems. And that has been the idea of say the CBAS preconditioner.
So from that idea you can also apply it, for instance, to mixed type problems like Stokes, or later on non-symmetric mixed type like Navier-Stokes or a Clemens equation. So basically what you would do by that same idea is that whatever the conditioning systems SU and SP, which would be the preconditions for the velocity and pressure blocks, would look like, this would be the structure of the system. So it starts off with a preconditioner for the, say, the velocity block, if that's what you would want to call it. That's a non-singular matrix by assumption, right? So it results from some elliptic operator. You precondition that thing specifically by S of U, that you would construct in the same way that you did before. Now, right, so the preconditioning of the velocity block is sort of, it's a no-brainer. It's just an immediate extension of what I already showed. But now the question is, how does one actually condition the pressure block? Well, after you've done the preconditioning of the velocity block, you can sort of figure out what you would want from the precondition for the pressure block. Basically, it would have to satisfy this condition. So if you would be able to construct an optimal preconditioner, that would mean that the inf sub of this matrix would be equal to the sub sub. That would be equal to the norm. And you can, that's in one of the most recent papers, you can figure out that you, in that case, if you would be able to construct such an optimal precondition for the pressure block, that the conditioning number would in fact be square root of 2. So this is just part of the analysis step. But basically it tells you what the form of the pressure preconditioner is. So the transpose of the SP times SP itself should be a preconditioner for this matrix. So that means that it's a preconditioner, in fact, for this matrix, and that determines what the pressure preconditioner looks like. So now if we do the same experiment again, then what you would find is actually that both for a second, say, quadratic and cubic approximations, without the preconditioner, this is what the conditional would look like. With that CBAS preconditioner, basically it's under control, irrespective of the cut that you make. Also for Navier-Stokes, right? So basically now we're not restricted to symmetric matrices anymore. The philosophy also applies to non-symmetric systems. So before I go to the summary, maybe one thing to point out is, of course, what Clemens just mentioned is that many of the things you can, of the conditioning issues, you can just resolve by doing ghost penalties, in fact. So you could question, if you do the ghost penalties and you do it properly, you figure out, say, what the parameter should be like. Do you still need preconditioning? Because, in fact, you're shooting with two guns at the same problem in some sense. But the preconditioning will still serve you, right? So basically what you would find is that otherwise you would, in the ghost penalty method, you could be sensitive to the choice of the stabilization parameters. If you combine the two, right, so you do the ghost penalty stabilization and then you still do the additive Schwarz, the connectivity-based additive Schwarz preconditioning, you're way less sensitive to the choice of the stabilization parameters, for instance. So it's worthwhile to do both. Now let's go to the summary. So basically, bottom line is that the main issue with cut element methods or FCM type approaches, especially if you go to high order, is this type of scaling. Right? So it does not depend on the mesh size of the background mesh anymore, but it now depends on volume fraction of the smallest cut element, and it scales terribly with minus 2p. So that's a very, very bad scaling. What we've noticed is, so the theory is just for the Laplace operator, but what we've noticed that in practice is that this 2p scaling extends to a large class of problems, a large class of second order PDEs, including elasticity, Stokes and Navier-Stokes. The main issue is, of course, that it has to do with the behavior of the elliptic part of the operator. I mean, that's where it comes from, and that's what all these PDEs have in common. Diagonals Diagonal preconditioning, so rescaling may resolve many problems, but not all, especially for higher order Lagrange or these IGA type approximation spaces. Because the issue is not only yield conditioning, it's also the near linear dependence which you could have on elements. Diagonal scaling and local orthonormalization, that's say the basis of the specific preconditioning, is effective and efficient for SPD systems. It basically resolves all the issues that you would have there. The extension to non-symmetric systems and mixed problems is the connectivity-based additive Schwartz. And that resolves the conditioning issues actually for a very large class of problems. Preconditioning of mixed systems can be based on the CBS of the Schur complement. That's what I showed. So basically we've been able to extend this idea of how to construct a preconditioner to a rather large class of problems. So we were asked to also have an overview of say the state of the art and the challenges. This would be where I summarize what I've shown and also what Clemens has shown. So what we have at TOE at the moment is we have a versatile open source Python implementation. It's called Noodles, which we can run for moderate scale problems up to a few million DOFs. Depends a bit on the problem. With applications to elasticity, Stokes and Navier-Stokes, so we will do all of that in the immersed setting. We have an image-based analysis workflow for voxel data. That's what Clemens showed. So basically, we are to a large extent capable of importing data from CT, FIB7 type scanners, any type of voxel data, and extract from that directly this via what Clemens showed, this type of computational geometry on which we can do the computation. We have a robust boundary parametrization technology in 2 and 3 dimensions. It's taken quite a lot of time to put it into place, but now we actually buy this type of desolation technique of the boundary. We have a very accurate and robust representation of the cut boundaries. We have a detailed understanding of the conditioning issues that arise for a large class of problems and also ways to solve it, either preconditioning or by means of stabilization or both. We have not fully exploited that, but we have a computational framework for error estimation and adaptivity, also goal-oriented. We've not really been exploiting that yet in the context of immersed, but it's available and it's on our to-do list. Of course, that's what we have available now. That's our state of the art. There's several challenges still remaining, especially in the immersed context. Mostly connected, I would say mostly connected with geometry. If I could use just a single word to indicate what the issues are, it's geometry. So that translates on the one hand into the integration procedures. Right? So because we have the cut cells, we need to do integration on the trimmed elements. The bisectioning with tessellation, I think it's one of the most refined integration schemes around. But still, it's too expensive for high fidelity computations, particularly in 3D. I'm not sure if we have that as a separate item, but the issue is, of course, we can do high order approximations now, and this scheme is at best second order accurate. And so if you basically, that means that if you're going to bump up the order of your approximation space, you need to go deeper and deeper down into this tree in order to do the integration. And that becomes too expensive. So the further analysis is required to gain insight into how to relax the integration on the subcell levels. Simultaneous refinement of spaces and geometry. So what I mentioned is, so one of the nice things about this type of technology is you have this disconnection, if you will, between the resolution of your geometry on the one hand and the resolution of your finite element space. So you can sort of mix and match them, which is sort of nice, but of course it twists your arm to do both optimally, right? So it's not like you can do both separately in terms of the methodology, but in terms of the approximation, you would want to do them hand in hand in such a way that you, for a given computational effort, you have an optimal approximation. And as I mentioned, so the representation of the domain boundary is at the end of the day still linear. And we have observed the fact that it that's the thing which actually restricts the asymptotic convergence rate. Subcell geometry regularization techniques are required to retain optimality. I think there's really a lot more work to be done there. Something which is open with respect, but that's something we have been discussing recently, is also, at the end of the day, it's because you have this connection to an inexact geometry, it's like it is like an inconsistent method. So what you have is, of course, in many cases you will be interested in computing functionals afterwards. If you have conforming methods with exact geometry, you have this nice Verhoosel-Miller lemma, which tells you that you have superconvergence for functionals of the solution in the finite element method. Basically, if you have a consistent approximation in this case, because you're essentially inconsistent, you will not obviously have Verhoosel-Miller. So your post-processing results may be way worse than what you have for a conforming method. So one question would be is how does that actually behave, and the other one is because you can sort of anticipate that that's going to be an issue, how do you actually resolve that? And so the main statement is that even if you control the approximation reasonably well in terms of the norm, right, so you would manage to get your representation of the geometry in such a way that the convergence in the norm is, say, as good as you would have for a conforming method. That does not mean that the convergence that you have for functionals that you would extract from that solution is as good as you would have for a conforming method. That's something to look into. And then, of course, if you want to apply to different application areas, there's quite a few things which require reconsideration. So something that that interests us is transport on the immersed boundaries. For us, that would be in connection with the inkjet printing applications. And then surfactant transport on the surfaces. And the other direction in which we want to extend it is flow through nanoporous materials, and that would provide a connection to kinetic theory. The reason for mentioning that here is that basically it's a different class of PDs that you're going to consider. These systems will be hyperbolic. So to my knowledge, there's not that much around for immersed systems for hyperbolic PDs. So if you're going to extend it into different directions, many of these things will require reconsideration. That sort of summarizes the challenges that we see on our end. And that concludes our presentation.